All right, the next operator that I want to discuss is the divergence operator, which is another derivative, and that typically is represented with this nabla operator and then the dot product to something, or divergence is also just written div for the divergence. And again, we have different definitions for the scalar, sorry, for the vector field or the tensor field. So remember that for the gradient operator, we took gradient of a scalar field, and that gave us a vector field, and the gradient of a vector field gave us a second order tensor. And then the divergence is gonna lower the order or the degree of our tensor. So if we have a second order tensor and we apply the divergence, we're gonna get back a vector. And we have a vector and we apply the divergence, we'll get back a scalar. For example, so divergence applied to a vector field, to a vector field B. So in that case, we have divergence of V, and that's going to be defined by taking the gradient of V and then doing this double contraction with the identity tensor, or alternatively, you can say that this is the trace of the gradient of V, and then this will be equal, if you have the components, this will be equal to the derivative of each of the components with respect to each of the coordinates, sum. So this I repeated, so this is sum over I. So notice that I have a vector in, but the out is a scalar. Even though I have components, because I'm just summing the components, I have a scalar. So that's it. That's the definition of the divergence of a vector field. Then what happens if I apply to a second order tensor? And then, as I said, I'm gonna get a vector field. So the divergence of a second order tensor is gonna be a vector field where I'm gonna take the partial derivatives of the components of t in the basis ei directly j, and then I'm gonna basically get rid of one of the basis vectors. So I have second order tensor in second and here I have a vector, right? And the vector has components d, dij, dxj. And here, notice that I have a sum over j is implied here. And let's use the definition of the divergence to do some identities. So that's it. Oh, that's all I wanted to do about the divergence. Lowers the order of the tensor. So we have a vector, we end up with a scalar. If we have a second order tensor, we end up with a vector. And these are the definitions. So let's do some identities. And this is a good way of also practicing, again, the initial notation. So what happens if I have the divergence of, similar to before, a scalar field multiplying a vector field? And so we'll start with putting this in the basis. So this will be this is a scalar, right? So this is a vector field, vector in, scalar out. But now the scalar is given by the sum of these derivatives where we have a product of two things. So alpha and vi, so we have to use chain rule or product rule. I guess I said chain rule last time, but it's product rule. So if we use the product rule, again, what we're gonna get is we're gonna get vi partial of alpha with respect to xi plus alpha dvi dxi. So that's the identity, but let's try to get back to the tensor notation. So can we make sense of this by, because this we still have so here these are components of V in the basis EI, right? So we still have the notion of a basis. So here we have VI are components of V in basis EI. But what if I want to go back to just tensor notation? So what's happening here, for example? There's a VI here, which makes me think of, so this makes me think of V, right? And this other one right here makes me think of gradient of alpha. And then here, this one doesn't make me think of anything. This one just makes me think of alpha, but this one makes me think of divergence of V, right? And here the fact that you have this I repeated here hopefully makes you think of dot product. So you remember that the gradient of alpha is a vector. So now you have Vi, so the components, the ith components of the vector V and the ith components of the gradient of alpha. So in reality what we have here, we have V dotted with the gradient of alpha plus, and here we have just alpha scaling the divergence of V. That's it. So that's back to the definition without a basis. So the divergence of alpha V is just V dotted with gradient alpha plus alpha scaling the divergence of V. So this is one thing, or components. Well, yeah, in components, there's no, this is a scalar, but I can express it in terms of the components of V. So that would be the scalar that is Vi d alpha dxi plus alpha dvi dxi. Either one would work. So that's one. Let's do the divergence of alpha times the tensor T. I have a tensor in. I am going to get a vector out, and that vector is going to be, if you just go back to my definition, this is going to be partial of alpha Tij with respect to xj, ej. EI, sorry. Otherwise I will have 3j. So this is basically what I had here, but with an extra alpha. And again, product rule. So I can split this into, so I can take the derivative, so I can do Ti j d alpha dxj ei plus alpha d Tij dxj ei. So that would be one of the answers, so that would be in components. This is perfectly valid. This will be the divergence of alpha t. But let's try to get back to the not component part. And so here, this is nothing but the divergence of the tensor t multiplied by alpha. So I think the second term on the right hand side doesn't have much to do with it. But the first one is a little bit nicer, right? So we have Tij, and then we have the alpha dxj. So actually I'm gonna keep this one right here. And now let's see what can we do with this one. Tij d alpha dxj ei. So this one should make you think of gradient of alpha, right? And then the fact that we have, and this is a vector, and the fact that we have Tij and then a j here, this should make you think of t applied to the vector gradient alpha. And then this is because, recall, for example, if you have tensor and you're applying to a vector, then in components, this will be Tij uj ei. right? So this looks very, very similar to what we have here. So this is just the tensor T applied to the gradient alpha. And then the other one is, as I said, there's nothing much to it. So alpha dTij dxj ei. I mean, this right here looks exactly like divergence of T. So then this one is just alpha times the divergence of T. And so basically what we have is the divergence of alpha T is T applied to the gradient of alpha plus alpha scaling the divergence of T. And that would be without components. Let's do one more. So what if I want to do the divergence of T applied to a vector V? So in components, this would be T, and now this is a vector. So I'm gonna get a scalar at the end of the day, right? And so what is the vector TV? That would be just in components, it would be Tij Vj Ei, right? And now taking the divergence of that just means having this extra partial with respect to xi. So this is a scalar where I have sum over I and sum over j. And now again, I'm gonna use the product rule for this one. So this would be Vj partial of Tij with respect to xi plus Tij partial of Vj with respect to xi. So that's it. This is one of the identities in components, using the components. It's a scalar, so there's no basis right there. This is a scalar, but it's still expressed in terms of the components of the tensor and the vector v. So what if I want to go back and not have, Tij or Vj or Vi? I just want to have, vectors and tensors. So let's see what is each one of these. So here we have, what is this Vj d partial Tij partial xi? So this looks like a gradient of this looks like the divergence of the, almost looks like the divergence of T, right? Why is it not the divergence of T? Because in the divergence, we have Tij with respect to xj. So that would actually be the divergence of T, right? So what is this partial Tij with respect to xi? That's actually the divergence of the transpose of T. So this is actually the divergence of the transpose of T. And then once I have the divergence of the transpose of T, the indices that I have left are these j's and j's, and that would be, you should think of that as dot product. So there's like this j makes me think of dot product between V and the divergence of T transpose. So this term actually comes from V dotted with the divergence of T transpose. So that's one of the terms. And then the other term is this Tij d Vj with respect to xi. And this one is also kind of interesting. So this one has the tensor ij and then something with ij here. So this one should be making you think about this A double dot with B, right? Which we said had components Aij, Bij, right? So this was a scalar. And it was obtained by summing basically the pairwise product of the entries of the tensors A and B. So that almost looks like this. I have Tij, right? So this looks like I'm gonna have T double contracted with this dvj dxi, and this one almost looks like, so almost looks like gradient of V, right? But the indices are sort of out of place. It should be the other way. So actually this is the gradient of V transpose. So this will be actually T double contracted with the gradient of V transpose. So going back to my initial thing that I wanted the divergence of T applied to V. And that one is going to be either this definition here in terms of the components, which is actually what you would use for computing in Python, because in Python you would use the components, but if you want to express it without a basis, then you can go back and try to replace these indices with something that doesn't depend on the basis. And then what we said is that the first term is going to be V dotted with the divergence of T transpose, and the second term is this T double contracted with the gradient of V transpose. So that's an alternative definition just in terms of vector operations. And the last one that I'm gonna do is what happens with the divergence of U dyadic B, so the tensor product. So then I have, second order tensor in. I'm gonna get back a vector because the divergence of a second order tensor gives me a vector. And if you wanna put it in terms of components, this will be the U dyadic V from the other video. This will be have components Ui Vj with respect to Xj Ei. So that's just my definition. Again, I'm gonna use the product rule. So this will be Vj dui dxj ei plus ui dvj dxj ei. And that would be fine. This will be just in components. This is fine. But again, what if I want to go back to something that doesn't depend on a basis? Then I need to get rid of the componency. So what is Vj dui dxj? Well, this one should make you think of gradient of U. Actually, it's exactly the gradient of U. And then when you see now gradient of U, and let me just arrange differently, because these are numbers, there's nothing against me arranging them in this order, right? So if I look at this sort of like this, then I have Ij, Bj. So this should make me think of applying a second order tensor to the vector V, right? So second order tensor applied to vector B. So yeah, indeed, this is nothing more than gradient of U applied to vector B. So that will be the first term. Then let's think about the other term. We have Ui dvj dxj ei, right? So this term right here, dvj dxj, should immediately make you think of the divergence of V. Right, so it's a scalar, and that's just it. It's the divergence of V, and it's what is it scaling. So if you rearrange a little bit, so this will be d vj dxj multiplying ui ei, right? So this is the vector u. So this is nothing more than the divergence of V scaling the vector u. So going back to no components, so the divergence of u dyadic B is going to be the gradient u, which is a tensor, applied to the vector V. So overall that gives me a vector, plus the divergence of V scaling the vector u. So this is a scalar, and this is a vector, so that's fine. And this is a second order tensor applied to a vector that gives me another vector. So I do get a vector out, so that would be fine. And that's it. That's the other way of writing it.